Now we're going to talk about instruction set architectures, and this is going to be the first of 2 lectures on it, so we're going to try and cover the basic parts here, and in the next lecture we're going to cover more details. So we're going to start out today with a review of how a program executes from the previous lecture. We're going to talk about the different types of instructions you have in MIPS. Then we're going to start getting into some details. We're going to talk about how MIPS look as memory and how you access memory. And we're going to start talking about instructions. Talk about 3 main classes of instructions. First, data operations. These are addition, subtraction, and multiplication. Then we're going to talk about data transfers. So this is how do you get data from memory into your registers. And then finally we're going to talk about sequencing. That is, how do you control the flow of your program? This is branches and jumps. So let's review what we talked about last time. So how do you program a processor? So here we have a C program. It's a simple loop. While I does not equal 2, we're going to increment I. We're going to put this through a compiler and it's going to create assembly code. And here's some pretend assembly code which sort of illustrates what happens here. From that we're going to take the operating system loader and we're going to load it into the memory on the computer to execute it. So if we look at how this is converted here, we can see what's going on. So the instructions here, the I equals I plus 1, well, this is converted into R0 equals R0 plus 1. What happened here was the compiler put the variable I into register 0, and it's used the instruction to add 1 to that register. We can look at other parts of this code. We can look at the part while I does not equal 2. What we've got here is we're doing 2 things. We're checking if I equals 2 by subtracting 2 from it, and then we're checking to see if it's 0. And if it is 0, we're going to jump to done, and if it's not 0, we go on to another addition and jump around the loop. So this is sort of a basic feeling for how you create assembly language code. Now we're going to look at this in more detail. So in order to understand this in more detail, we want to talk about what happens in the processor. And we talked about this at a simplified level before. We're going to walk through that again now, and then we're going to go into more detail for the exact way how MIPS instructions are actually executed. So the first thing we do in the processor is we load the instruction. That takes the instruction from the memory and loads it into the processor. Then we figure out what operation to do. This is where the control logic comes into play. It looks at the instruction, decodes it, and figures out what needs to be done. Then we figure out what data to use. The data is going to come from the register file, so here the control is going to tell the register file which registers to use. We do the computation. The computation happens in the compute part of the processor, or the ALU, arithmetic and logic unit. And then finally the results of that are going to be sent back to the control, and the control is going to use that to figure out what the next instruction is. And remember, we need this feedback path so that we can do things like check if things are 0 and know whether we should go around loops again. So all the processor does is it repeats this over and over again until it runs out of instructions, electricity, or it crashes. In this lecture we're going to see a lot of the real details. So we're going to look at the MIPS instruction set assembly language in particular, and we're going to look at how it's executed. So let's take a look at some example MIPS instructions. So MIPS instructions generally are a 3-operand format. That is, there's an operation, a destination, and 2 sources. If you look at what this means, what we have is we're going to do some operation. So this could be an addition or subtraction. We're going to take the results of that and we're going to store it into the destination register. And the inputs that we're going to use to the operation are source 1 and source 2. So when we write op destination source source, you should think of this as destination is getting the results of source, operation, source. Let's look at some concrete examples. So here's addition. So addition is simple. Add A, B, C. And what is this going to do? It's going to store the results of adding B and C, the 2 source registers, into A, which is the destination register. Here's another example. Add immediate. Add I. Here we have A, B, and a number, in this case 12. And this is going to add the 2 sources, B and 12, and store them into the destination A. The I here is for immediate, and you'll see this in a lot of instructions in MIPS. Subtraction is similar. Here's subtraction, sub A, B, C. This is going to store into the destination A the results of B minus C. Now what if we want to do something more complicated? So here we have an equation F equals G plus H minus I plus J. Now MIPS is a 3-operand format. That means that we don't have any instructions which cover this entire thing here. So what we're going to have to do is break it up into 2 pieces. So first we're going to do the first half of it. We're going to do an add, and we're going to store it into a temporary value. So here T0 is our temporary value. We're going to store the results of the first half into this temporary value. This is just a register. Then we're going to do the second half. We're going to store the results of the second half into a temporary value, And then finally, we take those two temporary values, which are stored in two registers, and we use them as the source for the final subtraction, which then stores the results into F. So what you see here is that complex operations are going to generate a lot of instructions, and they're going to use a lot of temporary variables in order to break up those complex operations into simple operations that are supported by MIPS. Now there are three types of instructions that we're going to talk about: data operations, data transfer, and sequencing. Data operations, the sort of thing you've already seen: arithmetic stuff, addition, subtraction, multiplication. And logical operations such as and or and XOR are sort of the meat of the processing. This is where you actually do work and you compute results. Data transfer instructions are very important for getting the data you want to work on and moving it around. We have move instructions, which move data from one register to another, and we have load and store, which load data from memory and then store data back to memory from the register file. Of course, with just these instructions, we can't do much in our program. We also need sequencing instructions. We need ability to branch conditionally. That is, check, is something greater than or less than, or is it equal to 0, so we know if we're ready to jump. And jump instructions, which tell you just go somewhere unconditionally. So if we look at the program that we had before, this simple loop program here, you can see we already had a lot of these things. We had a load memory instruction at the beginning to initialize R0. We had loop instructions with an addition and subtraction, and we had a sequencing instruction to see if we were done, and a jump instruction to continue the loop if we weren't done. Here's a table of all the MIPS assembly instructions that you're going to be looking at in class. And as you can see from these are divided up. Here are the arithmetic options for add and subtract and multiply and divide. Here are the logical operations. Here are the load and store operations. Here are the conditional branch instructions, and then here are the unconditional jump instructions. You've got a convenient table of this printed in your textbook, so feel free to take a look at that while you're working on the labs. Now we're going to talk about registers in MIPS. MIPS is a register architecture, and it has 32 general purpose registers. These are typically labeled R0 through R31 or $0 through $31. And we think about them as one big linear file like this, where you can store values in the different registers. As you've seen in the examples we've looked at so far, all of the values for instructions have to come from registers. That's what it means to be a register machine. You need to store the values in the registers and then you can operate on them. Some of these registers are special. In particular, R0 is always 0. That means if you use this first register, R0 in the register file, it will always be 0. You can write to it, but your write won't have any effect. There's some other ones which are special. R29 and R31 are used for procedure return addresses in the stack pointer. These are important when you're going to make function calls, and we'll talk about that in the next lecture. So here's a question to think about. Why is R0 always 0? What benefit does that have? Why is it worth wasting one of your registers to always be 0? Well, the answer to this is basically that you always need 0 in a program. You're always going to have to check and see if counters get to 0 or need 0 for comparisons, so you might as well have 0 hardwired in so that you don't have to get it somewhere else in your program. 0 is also a very useful thing to use in architecture. So MIPS doesn't have a move instruction. Instead, what it does, if you want to move from one register to another, you use an add and you add 0. So if I want to move from a different register, I simply add 0 to the value I want to move and store it in the new location. So this makes having a hard-coded 0 very convenient. There are also a few special registers in MIPS, and the one that we're going to talk about most, and we're going to talk about a lot today, is the PC, or the program counter. This is the register that holds the address of the current instruction that you're executing. This is the one that tells you which instruction am I working on now, and when you want to go on to another instruction, you need to update this value. There are a bunch of other special registers also, which we're not going to touch on in this class. There's high and low for the results of multiplication, floating point registers, and a bunch of control registers, which you may use in the I/O lab later in the term. So the important takeaway messages here: we have 32 general purpose registers. When you're doing computations, all your values have to come from your registers, and some of them are special. So R0 is always 0, and you want to keep that in mind. Now we're going to talk about memory organization in MIPS. That is not your register file, but your main memory and how it's organized and accessed. So memory is organized as a large one-dimensional array. Each location in this array is 1 byte, or 8 bits. So we can draw a picture of it like this. It looks a lot like a register file, but it's much, much larger. Each entry in it is 8 bits of data. A memory address is used to index into this array. So we assign each of these locations in the memory array an address. So we start at 0 and we go all the way up to the full size of the memory, which for this machine is going to be 4.2 billion. Each one of these addresses points to a location in the memory array, and we identify where we want to get in memory by this address. So if we have a 32-bit computer, that means there are 2 to the 32 memory locations, or 4 billion, 4 gigabytes of data. If we have a 64-bit computer, there would be 2 to the 64 memory locations, or 16 exabytes of data. So the bitness, if it's 32 or 64 bits of a computer, determines how much memory it can address. Now, in reality, nobody has a machine that can access 16 exabytes of data. It's tend to be limited to much less than that. So now we're going to talk about memory words. I just showed you a picture of memory, which is a nice one-dimensional linear array of bytes. This is very convenient, except almost everything in MIPS accesses data in more than 1 byte at a time. Most of the data is accessed in words, and a word is 4 bytes or 32 bits of data. So the view that we were just talking about before is the byte addressable view of memory, where each address points to a unique byte in memory. However, when we talk about words, we're going to put addresses together. So here's address 0, 1, 2, and 3. We now have 4 bytes of data, or 1 word. So most of the operations that you're going to do to memory are going to focus on sizes of 4 bytes, or 1 word like this. Now if we look at data from this point of view, we can see that our addresses now go 0, 4, 8, 12 because each address is pointing to the beginning of 4 words of data. This word address gives us access to memory in a word-aligned view. That is, we're looking at memory as if it's aligned to words. Now, this may seem confusing. Why are we sacrificing the nice simple view of memory where each address points to 1 byte to this idea where each address points to a word, and if it's aligned, it points to the beginning of the words? Well, the reason for this is most things in MIPS hold words. So registers each hold 32 bits of data or 1 word. Addresses are 32 bits of data or 1 word. So if we want to load data from memory and put it into an address, we want to get a full word of data to fill up that register. In our 32-bit machine, where we have 2 to the 32nd bytes of memory, we're going to have 2 to the 30th words. That's because each word is 4 bytes, so we have 1/4 as many. Here's a question to think about for the end of this section. What are the last 2 bits in a word address? So in a byte address, you go through every address, 1, 2, 3, 4, 5, 6, 7, all the way up. But in word addresses, you go 0, 4, 8, 12. What does this tell you about the last 2 bits in that address? So now we're going to talk about access alignment. Because we have this word-aligned view of memory, you can access it in different ways, some of which are nice and some of which are less nice. So aligned addresses fall on one of these nice 4-byte word boundaries. So addresses 0, 4, 8, 12 are nice aligned addresses. If I go to load a word at address 0, that's at the beginning of a full word, and so that's nicely aligned. So if I do load word address 0, I get an aligned access. If I have unaligned addresses, those are ones which are not on word boundaries. So 1, 3, 7, 63, all of those will be unaligned accesses. So if I go to load address 9, this is going to be unaligned because the word of data at address 9 is not aligned to 1 word in memory, it splits across 2 of them. So this is a not aligned access. The reason you care about this is some machines support unaligned accesses and some don't. MIPS does not support this. And the reason you might not support it is it's complicated. So if I want to support unaligned accesses, I have to have hardware to clean this up. So for loading address 9 here, the hardware would have to say, well, I need to load this aligned word first, then this aligned word, then I need to pull out the right parts of it and combine them together. That's complicated to do. You could also do this in software. You could have the hardware detect that it's a non-aligned access and have software fix it, but that's going to be very slow. So there's typically a performance penalty for accessing unaligned data, and this is why sometimes unaligned addresses are not supported. So in MIPS you can only do aligned accesses. To put this into perspective, Intel didn't give a high performance support for unaligned access until 2010. So this was a long time before Intel was able to make their processors do unaligned accesses quickly.